Right, good afternoon, everyone. I'm Massood Atashbar from Western Michigan University, and I'm presenting my PhD student work who could not be with us, Mr. Arnesh Bose, and his work is development of flexible microplasma discharge device for sterilization application. And with that, this is the outline of my talk, and I will start the presentation to discuss the relevance of choosing Pseudomonas aeruginosa as a target pathogen and go through some of the current sterilization methods and talking about a brief discussion about plasma and then microplasma-based sterilization, and then moving on to experimental, which what kind of material was used, how the fabrication was taking place, and experimental setup. And then we'll discuss the results obtained and conclusion and future work. So Pseudomonas aeruginosa is an opportunistic gram-positive rod-shaped biosafety level 2 bacterium, and it is one of the most common infection-causing bacterium in the hospital. And specifically for the individuals with weak immune systems, it is targeting those. And symptoms of this infection are like flu-like symptoms, skin rashes, pneumonia, blood infection, and in extreme cases, it can lead to death. And according to the CDC, in the United States alone, there is more than 51,000 of infection of this bacterium per year, and it is reported that more than 13% of those are drug resistant, and which result 400 deaths per year. Therefore, there's a need for developing a cost-effective alternative for sterilization of the wound and eradicating this kind of bacteria. So in order to sterilize the surfaces and other applicable different surfaces, including wound, but these are not used for wound, these are for instruments. There are steam and dry heat, chemical as well as plasma are the common sterilization methods and the disadvantages for steam and dry heat is such that they require very large equipments and they require special chambers so that they are not portable and they are expensive. For chemical sterilization, basically chemicals needed for these sterilization, if they are not handled properly, they can be a source of pollution, environmental pollution. And the other one for the plasma, basically they need chemicals like hydrogen peroxide as well as ethylene oxide, and they can leave chemical traces, and in these cases, since these chemicals are being used, again they require chambers, and which again they render to be not portable. So to alleviate the use of these chemicals and bulky chambers, microplasma-based sterilization methods utilizing air ambient as a sterilizing agent is being proposed and being developed. So plasma is one of the 4 fundamental states of the matter, and it is the most abundant form of matter in the universe. Plasma does not form in a natural state on the earth, and it needs high electric field to form the plasma, and it happens due to the ionization and deionization of the gaseous particles in a very high electric fields. The best example of the plasma is the sun, which there is a constant ionization of helium and hydrogen. Plasma can be categorized into 2 main categories or group. One is thermal, the other one is non-thermal. Thermal is the one that the electron temperature is the same as the surface temperature of the plasma. And in order to form thermal plasma, or it is called equilibrium plasma, their electrode gaps usually is more than 1 millimeter. For non-thermal plasma or microplasma, the surface temperature is less than the electron temperature, and in order to form those, the electrode gap distance is less than 1 millimeter. So that we are focusing on non-thermal since the surface temperature is lower, and we can be at around room temperature. Microplasma-based sterilization methods can be categorized in more subgroup. One of them is microplasma jet, and in this case, microplasma jet, again, at the nozzle, there is electrode to create a very high electric field, and since there is jet, there is a need for flow of the gas, and in that case, so that you need to have a control of the flow of the gas to form the glow of these plasma. And in that case, again, it is adding to the complexity of the system. Surface microplasma, it can be in ambient air or it can be in controlled chamber. When there is the control chamber involved, so again, it is making it bulky and more expensive. So our focus is using microplasma discharge devices and using air as a sterilization agent. For this, if we use microplasma and we don't use any chamber, we will improve the portability, and we will be using, since it is microplasma and non-equilibrium, we will have a low input voltage, and we will show that we have very comparable and in some cases amazing efficacy in terms of sterilization. For fabricating these devices, we are using laser ablation, and system that we are using is universal laser. And with this system, basically, we can have a high precision design, and we can replicate device to device. And if we can, with this system, depending on what kind of source of laser that we have, we can cut through metals or non-metals. If it is metal, we use fiber laser. If it is non-metal, we use carbon dioxide laser. And this particular system for the cutting metal, fiber laser has a wavelength of 1.06 micrometer, and so we can control speed, frequency, and thickness that we can cut through. In order to fabricate these devices, materials that we use, we start with substrate, which is PET from DuPont film with a thickness of 50 micrometer, and we use 2 mil copper tape with a thickness of 2 mil or 50 micrometer, 50 micrometer, and with the width of 4.5 inches. And we use 1 mil single-sided Kapton tape as a dielectric and also as a passivation layer. And we use crimp connectors for electrical connectivity. In this slide, it is showing the fabrication steps, so that this is the PET substrate, which we clean it with IPA first, and then sticking the copper tape on top of the PET. Then we go through transferring the pattern that we have for the top electrodes on the top copper, and then we attach the Kapton tape on the back to take care of any hole or a perforation that may have happened due to the laser ablation that we have, and then attach the copper tape on the back for the back electrode, and then going through the ablation for the back electrode. This slide is showing the side view and top view of the fabricated devices. The top electrode is honeycomb shape, and we are using honeycomb shape for a uniform distribution of the voltage, and on the back is the counter electrode or back electrode, and on the right it is showing the fabricated devices And on the right side of the right figure, it is showing the actual microplasma when the device is on. And as you see, the intensity of the microplasma that we have is uniform across the device. So we have done surface temperature profiling using thermal camera, and with different voltages that we apply, we have measured the temperature of the surface. And for 4 volt to about 10 volt, we have done the characterization, which the temperature ranges from 26 to about 70 degrees centigrade. And our aim is to bring the system to operate around 40 degrees centigrade, so not to be too hot. However, we will see that even if it is at around 60 or 70 degrees centigrade, it's not a problem. In order to do the test, here is the bacterial sample preparation, which we use liquid Bertoni, LB or agar, in order to form and grow our colonies. And we pour these onto the Petri dishes with a height of 15 micrometer. And then we go through serial dilution and strict plate to form different concentrations of the colonies. And here, for example, is 10 to power minus 1 all the way to 10 to power minus 8. Here is 10 to power minus 4. And after we introduce this bacterium to the substrate or to the agar, then we have to incubate it for 24 hours to grow the CFUs. And in this case, this is the starting one, and here is for the 10 to power minus 4 dilution was used as control, which when in the following slides, when I'm using term control, it means that 10 to power minus 4 dilution has been used. Here is experimental setup, which we have a power supply, and it is connected to the step-up inverter, and then microplasma discharge device, and then we have the Pseudomonas samples. So that here is the microplasma that it is sitting on the surface, and in this case we are putting our Petri dishes inverted on the top of the microplasma device that we have in this case. And we are running our experiments for very different voltages, different heights. When I'm stating height, it means the gap between the electrode and the agar surface, as well as different time for the treatment. So in this case, in this slide is showing varying gap distance, and again, this is control with the dilution of 10 power minus 4, and the distance is 1 millimeter, 3 millimeter, 5 through 9 millimeter, and as it can be seen here that after doing the treatment, we go through incubation for 16 hours for 37 degrees centigrade to see that any of these bacterium that we have here was survived or not. And in this case, the voltage applied is sample 5, and as you can see, all of these, in fact, have killed all the bacterium. So that in this case, we have 100% efficacy. And this slide is showing gap distance of 4 millimeter, and here is the control with number of CFUs that we have for 10 second, 20 second, 30 second, up to 60 second, and then steps of 1 minute we have gone up. So in this case, for 10 through 50, the efficacy is about 99.9%, and from 60 and above, it is 100% efficacy. So there is no single colony has survived with such a gap distance as well as input voltage that we are applying. This slide is showing varying input DC voltage, and from voltages from 1 volt through 5 volt, we were not achieving sterilization. At 6 volts, we had partial sterilization at 7 volt and above. At 7 volt is more than 99.9%. Basically, we have 3 colonies survive, and any voltages above that, again, is 100% sterilization efficacy, which is achieved. This slide is showing constant treatment, and gap distance is 4, but we have variation of the concentration or dilution. So it is 10 to the power minus 1, minus 3, and minus 8, I believe. And here's pre-treatment, after treatment, so that after you're going through this treatment that I have shown here, again, going through the incubation, and as you can see, none of the bacterium has been survived, and no CFUs can be found. In conclusion, basically we have developed flexible microplasma discharge and was fabricated using laser ablation, and so that it is flexible because the substrate is flexible and we can bend it, and it is conformal, so that we can make this structure to have a very simple system to put it on the top of the wound that is not healing by itself, so that we can quickly sterilize the wound in that case. And we can achieve efficacy of about 100%, and generally the efficacy is the range that we have been achieving, 99.9 to about 100%, and in most of the cases 100%. And future work that we have is to focusing on enhancing the capability of the fabricated devices, performing variation of the curvature and bending that we have, and focusing on other gram-negative and gram-positive bacteria like Salmonella, Bacillus subtilis, as well as Staphylococcus aureus bacterium, to expand the and showing the efficacy of this system. Any question?
Okay, thank you.